In Chapter 10, we're going to introduce two different kinds of coordinate systems, one involving parametric equations and another involving polar coordinates. So the first two sections will involve parametric equations. In 10.1, we're going to focus mostly on what parametric equations are and what we can do with them. So what is a parametric curve? A parametric curve is a curve that you can imagine here can take on sort of a winding path through the xy plane, where each point of that curve, xy, is determined by some function f of t for the x coordinate and some function g of t for the y coordinate. So we can imagine that as the parameter t increases, the point xy will travel through various different values in the xy plane. So one way to picture it is it's describing the motion of this particle as the parameter t increases. So sometimes it might be helpful to think of t as a time parameter, where as time increases, the point that's in the xy plane will take on a different location, and it'll describe the trajectory or the path of this particle. So let's think about some examples. Suppose I want to sketch the curve that's defined by the parametric equations x equals t squared minus 2t and y equals t plus 1. One way to do it is to imagine we're just going to make a table, and we look at the x and y coordinates for several different values of t. So we can imagine t here just takes on a variety of different values. So here I'm picking some values that we can use to evaluate x and y. So we'll just make this table of values. And then filling it in here at the various different values of t. So negative 2 squared minus 2t. We would have an x coordinate of 4 plus 4 is 8. And then negative 1 squared minus 2 times negative 1 would be 1 plus 2 is 3. And then 0. And 1 minus 2 is negative 1. And then 4 minus 4 is 0. Okay. For the y coordinate, we'll have negative t plus 1, or sorry, negative 2 plus 1. So that will be negative 1. And then 0, 1, 2, 3. Evaluating t plus 1 at these various values of t. So you can see here that those correspond now with a collection of xy coordinates. So when we plot these coordinates, we can get an idea of how the parametric curve is traced. So starting with the point that we started with at t equals negative 2, at 8, negative 1, and then at t equals negative 1 we had 3, 0, and then at t equals 0 we had the point 0, 1, and then at the point t equals 1 we had the point negative 1, 2, and then when t equals 2, we had the point 0, 3. And so we can see that the curve is going to be traced out this way. You can imagine it would continue. And there's a particular direction associated with this curve, because we see as the parameter t increases, it's going to travel through these values that we plotted. So the direction that the curve is oriented is another thing that we can consider when we're thinking about parametric curves, is that there's always a particular direction that the curve is being traversed. And in this case, we didn't give any restriction on t, but that could also be something that's indicated. For instance, if I put the restriction -2 to 2, well, those would be the points that we graphed here. So that would just be this portion of the curve from here where the parameter was at t equals -2, t equals -1, t equals 0, t equals 1, and then it ends here at t equals 2. So it's got a starting and an ending point if we're specifying what parameter is t. So it has this starting and ending point. But in general, if there is no indication, we can imagine this curve would be traced through all values of t. It looks to me like this maybe is a parabola, like a sideways parabola. So is there a way to show that? So one way to do that would be to try and find a Cartesian equation of the curve that's defined by these parametric equations. To find a Cartesian curve, we're looking for an equation in the x and y variables. So when we say Cartesian, another name for it is rectangular coordinates, but Cartesian means that we're looking for an equation in x and y. So the process that we can do is we can do something called eliminating the parameter. And one way to do that is to try and combine these two equations together by removing the parameter t from the equations. So if I've got y equals t plus 1, for instance, I can easily isolate the t, and then I can replace that t in the other equation. So if I've got x equals t squared minus 2t, I can replace t with y minus 1. And now I have my Cartesian equation in terms of an equation in terms of the x and the y variables. And we notice that, in fact, yes, this is a sideways parabola. It's a quadratic equation in the variable y. What about a curve where we have x equals cosine t, y equals sine t, where t goes from 0 to 2 pi? Well, we can kind of remember that this is essentially going to trace out the points on our unit circle. We know when t is 0, we get the starting point here would be 0, 1. And as the parameter t goes to 2 pi, or sorry, goes to pi over 2, then it's going to trace the curve up till the point here at 0, 1. So at pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. So there, just between t equals 0 and t equals pi over 2, it's traveled through the first quadrant there. And then as it travels from pi over 2 to pi, it's going to trace out the curve here in the second quadrant. So at t equals pi, notice we'll get the point -1, 0. And then from pi to 3 pi over 2, it'll continue to trace out the curve here through the third quadrant, and then from 3 pi over 2 to 2 pi it'll finish the curve there and complete the whole circle. Okay, so there we sketched it simply by plotting a couple of these points that are between 0 and 2 pi. So visually we can see that it's the circle of radius 1. Let's try and eliminate the parameter to also see that it's a circle of radius 1 as a Cartesian equation. So one way we can do that is we can remember this basic identity, cosine squared t plus sine squared t equals 1. Or of course we know cosine is actually equal to x. So this would be x squared, and sine squared would be y squared. And of course here we have the Cartesian equation of our unit circle. Okay. And then what if we had a slight variation of this, where it's x equals cosine 2t, y equals sine of 2t, and again still the same t going from 0 to 2 pi. Well, one thing we can observe is that it's going to pass through those same points that the other curve did before. So it's going to go from 0, 1 to, or 1, 0 to 0, 1 to negative 1, 0 to down here at 0, negative 1, and then back to 1, 0. But it's going to do it twice as fast. So in other words, if we notice that just going from 0, t equals 0, to t equals pi over 4 now, right? When t equals pi over 4, then I get cosine of 2 times pi over 4 is cosine of pi over 2. So that gives me the point at 0, 1. And then here at t equals pi over 2 is when it's going to wind up here at the point negative 1, 0. And then here at t equals 3 pi over 4, it winds up here at the point 0, negative 1. And then back to 1, 0 at the point t equals pi. So that's only halfway around. It's going to actually continue to do one more rotation. So it's going to go through those same points again in a second loop. So it's going to essentially traverse this unit circle twice at a rate that's twice as fast as the previous one. So it's going to again cycle through those same points again. Here this would be at 5 pi over 4, it'll come back there. At t equals pi, it'll come back there. T equals 7 pi over 4, it'll come back here. And then at 2 pi, it'll wind up back here one last time. So you see it's the same unit circle, but the circle is traversed twice at double the rate as before. So we can imagine what's happening here is that when we're multiplying 2t, the parameter t is being doubled. So it's going to speed up. It's going to go through those same points again at twice the rate. So suppose we wanted to find the equations of a parametric of a circle with a center at hk and a radius of r. Well, we can take the equations that we had before. So we know that x equals cosine t and y equals sine t. Gave us a circle of radius 1 centered at 0, 0, 0. So if we want to increase the radius, one way we can do that is we can multiply sine and cosine by a constant. So if I do x equals r cosine t, y equals r sine t, that's going to give me a circle of radius r. Still centered at 0, 0. Right? Because we noticed now that if we look at the equation x squared plus y squared, well, here we've got r cosine t squared plus r sine t squared, which we can factor out r squared, and then we're left with sine squared t plus cosine squared t, which we know is equal to 1. So it's just r squared times 1. So here, these two equations here are going to give us the Cartesian equation, x squared plus y squared equals r squared, which we know, of course, is a circle of radius r. And by the same trick here, if I wanted to get a Cartesian equation that has a center at hk, well, we want it to be of the form x minus h squared plus y minus k squared equals r squared. That's going to give us a circle with a center hk with a radius of r. So therefore we can adjust it slightly here. So I can, if I let x equal to r cosine t plus h, and then I let y equal to r sine t plus h, then we see that x minus h would equal to r cosine t. So then that would give us this equation here, r cosine t squared. And then y minus k, sorry, this should be k, not h. So y minus k would be equal to r sine t. So I would have an r sine t squared here, which would give us that term of the equation there. So this would be then the circle of radius r centered at hk.